I'm Werner Wagner. I work with Sika for 15 years now, and I'm now in this business for 25 years. I started with R&D, product development and technical service, and meanwhile I'm in marketing and market field manager. Are you looking forward to the farewell party? Yeah, me too, me too. So I thank you very much that you found the way to this presentation and you joined me in this presentation about extreme conditions for structural sealant glazing. And what can be more extreme than bomb blast scenarios? When we talk about structural sealant glazing, I'm sure you are thinking of one particular sealant, and this is silicone. You name it, silicone. And it had good reasons. When structural glazing made it into the market in the early 1970s or late 60s, that was really the one and only adhesive which was UV resistant enough and thermally stable. And that was the reason why silicone was the choice then. And when at that time also the, let's say, the shading opportunities and temperature control was very limited. And therefore we used the silicones. And when we look into 2019, it's still the silicones. Yeah, for sure. We don't have any other options, yes, in terms of UV stability for the time being. At that time, there were still simple construction, little shading devices. But meanwhile, the building industry, the facade industry, had to deal or was able to deal with alternatives, with smarter, the buzzword smarter, with smarter technologies. First of all, it was the introduction of the insulating glass unit, and especially in this device here, in this situation, there is almost no direct sunlight, no direct sun radiation to the bond line. Next comes the PVB interlayer. One interlayer absorbs about 95% of the UV radiation. Yeah? So it's not directly exposed anymore to the bond line, to the UV. Then we talk about thermal breaks. For example, in this particular situation here, the thermal break here prevents a direct thermal conduction of the heat here to this bond line. Then we talk about climatic control systems, especially when it comes to these shading devices here. That also helps a lot to get the temperatures under control and also the UV radiation. Then on top of that, we talk about ceramic printing. Meanwhile, we don't talk about screen printing. We don't talk about screen printing anymore. There are digital printing opportunities, which makes it much easier to put on a protective layer on that. And last but not least, we have software for building physics to evaluate, to predict extreme conditions and to prevent extreme temperatures in the system. So altogether, we have nice opportunities, valuable opportunities to get the temperature and the UV radiation under control. So we have smarter technologies, but with smarter opportunities, there comes more demands. Yeah? Today, we have very complex geometries. We are looking for high transparencies, and that means bigger glass panes. We can do that, but on the other side, we also are going for bigger joint bites. Then we talk about cold bending. it was worth a total session yesterday, talk about cold bend glass, and this here requests for, or this causes higher strengths, higher static loads, higher permanent loads. Then we come to these extreme dynamic loads under blast conditions. Fair enough to say that these are the most extreme conditions for the bond line. On top of that, we talk about this sustainability. It calls for new materials. It bans old, tried and tested materials sometimes. So this whole construction chemical industry is under, let's say, revision and under scrutiny. But all these demands here are answered with new technologies like this laminar bonding, as we call it, opaque facade panels, fixation for opaque facade panels, and the industry answers with new materials. And these new materials, it's not just the substrates the facade is built of, but we can talk also and think of new sealants and adhesives in the construction industry, in the facade industry. And when we look about these opportunities here, about epoxy or acrylic sealants, crash-resistant PU adhesives, here silicones and PU adhesives and PU sealants, you will notice quite a tendency from very high strength and rigid bonding to, let's say, lower strength elastic bonding. This kind of hockey stick does not go in this direction, what we would like to have, but it's a matter of fact that we have this kind of behavior. Then, when we talk about these silicones, here we are in this, I would say, almost in the worst situation. Yeah? We need the flexibility for elastic bonding, but the strength here is limited by the chemistry. 6 years ago, at the same event here at GPD, I presented a high-strength silicone, a development by Sika, moving this, let's say, the tensile strength from 2 megapascal to 3 megapascal. Hey, that sounds very limited and not very much, but it was for the silicone industry, for the structural glazing silicones, it was almost a little bit of a quantum leap. It was an increase of 40% of design strengths. But we would like to get in this area here and getting to higher strengths. And this is only possible when we think about polyurethane adhesives. Okay? That's a very provocative approach, but I think it's worth to think about that. When we compare the mechanical properties of a typical structural glazing silicone, a two-component silicone, we talk about 2 megapascal, and I have selected for a comparison a polyurethane from the transportation industry, from the train industry. And here we talk about a tensile strength of 6 megapascal. Okay, we know polyurethane have their limitations. UV resistance for sure. On the other hand, also temperature stability. And therefore, we have compared some results for structural silicone and polyurethane. And I would like to show you at the beginning as a start the behavior of silicone and polyurethane. So I think that's quite impressive. And when we look at the values, we have a almost 3 times higher tensile strength, 2.5 times higher elongation at break. So that paves the ground, that sets the environment for further tests. And we tested, again, then the lab shear strength, because we are talking about, I would like to drive this discussion and this thinking into the area of bomb blast testing, where we need high lab shear strength. So we tested it under standard conditions and did some aging testing. Then higher temperatures, because polyurethanes are also supposed to give in or to get weaker above 80 degrees, 90 degrees. That's almost a no-go. That's the common understanding of polyurethanes. Then fatigue testing, fatigue behavior, and last not least, how do polyurethanes behave under high-speed impact? So we have done a lot of tests, and first of all, we set it under standard conditions. And if you look at the structural silicone and the polyurethane, it does not look very different. But when you look at the right ratio, when you look at the right ratio here, silicones are working here. And this is the end of the polyurethane here. So that's quite a big difference, and I think it's worth to do more investigations on that. Then let's come to high temperature behavior. And we did it even after accelerated aging. And when you look at these bars, at the diagrams, if we compare even let's say the maximum what we can achieve with silicone and the minimum at high temperature with polyurethane, it's already a factor of 2, or it's still a factor of 2 times higher than the silicone here. And this was measured at 6 millimeter thickness. When we go to 3 millimeter thickness and we do more comparison at various temperatures, minus 35 degrees, plus 70 degrees, and we also compare the worst case for the polyurethane, the best case for the silicone, it's still 3 times a factor of 3, where the polyurethane outperforms the silicone. Okay? Then let's come to the fatigue behavior. Polyurethane is said that under fatigue, under cyclic load, it's not the best performer, but that really depends where you start from. And after 10,000 cycles here, this yellow range, polyurethane is even still 4.5 times higher than the silicone here. Then let's look at high-speed behavior. This is essential for the use in the bomb blast scenario here. And we have measured at 3 different speeds, impact speeds between 1 and 5 meter per second. And it's quite a common understanding that the glass reacts to the bomb blast impact with a maximum speed of 4 meter per second, but to be on the conservative side, we start at 1 meter per second. And when we look at this here, this 1 meter per second here, this is the test speed here and the lab shear strength. So here we have a factor of 3, and even under the worst condition here at high temperatures here, and this is the graph here comparing with this one, it's still the same ratio. So that means that at high speed, the polyurethane also performs better than the silicone. Okay, then this was the comparison of the lab shear strengths here. And when you look at the fracture energy, the work you have to apply to fracture the lab shear sample, it's even better. We have a 3 to 4 times higher value for the polyurethane. Let's come to a practical example. We got some values and some parameters from a customer with a maximum shear force for 91.5 kilonewton per square meter per meter at the highest peak. And when we calculate the joint bite, applying the tau at 1 meter per second, we come to a joint bite with silicones of almost 54 millimeter and with polyurethane of 23 millimeter. That's a significant difference. Yeah. So now let's look at the application. The mechanical strength, even under the, let's say, aging, was already to some extent convincing. Now let's come to this application, because this is also important for the production of the units. And we compare here a typical structural glazing silicone here. Okay. Structural glazing silicone, a two-part with an open time of 25 minutes. And everybody who has been in this business and in the workshop, you see there is a lot of room for improvement in terms of waste because of short open time and not really perfect production conditions for continuous productions. And here we compare this with a polyurethane, a monocomponent, accelerated, which is tried and tested in the transportation industry. And we have about 40 minutes of open time. So that's a nice approach here. And now let's come to the individual application itself. So a one-component polyurethane is used here, is applied here with a one-component gun, Unipack or sausage gun, or with a simple application machine. But here we would like to introduce to you this polyurethane with a booster. We call it booster because you have a Unipack here, a sausage with a booster paste, which is a paste-like water-containing agent. And this is used in a mixer, in a dynamic mixer. And the advantage of this is it's applicable as simple as a one-part material, but it cures very fast. It reaches the 50% of the final strength after 6 hours. And on top of that, we have a nice behavior here. There is no limitation, or I would say almost no limitation of the maximum joint size, joint bite. When you consider one part silicone, one part polyurethane, maximum joint bite is limited to 15 millimeter, 18 millimeter maximum. And here we can go to 20, 30 millimeter, 40 millimeter, as long as you can apply it properly. Okay, then let's look at these details a little bit more. The polyurethane here, the application is very simple here, and substrate, it bonds very well on glass, on ceramic frits, which is important then for bomb blast resistant glazing under these conditions, aluminium, metals, plastic. On top of that, it is really fast curing. It cures independently from humidity. It cures in deep joint. It's easy to use. It's a short mixer. It's ergonomic handling here with this gun. And with a minimal waste, it's eco-friendly. Let's have a look at these tried and tested applications here with this polyurethane. When you look at the parameters in the train industry, the size of the glass panes here, 2 meter by 1 meter 50. Yeah, that's very similar to a facade element here. The wind loads, 6 kilopascal. In Europe, you don't reach it that much. Yeah, in Asia, yeah, okay. But here, when two trains or opposing trains are passing in the tunnel at the speed of 250 kilometers per hour, we talk about a static pressure of 15 to 20 kPa. This will never be met in wind loads here in the pressure, in reality. And meanwhile, we have about 40 years of experience with polyurethane in transportation industry, in trains, bus, trucks, ships, and so on. Okay, let me summarize that. In the 1970s, the silicone technology was the only option that, no matter what, yeah? And it's still the tried and tested solutions. We also sell this, for sure. But I think as the facade technologies are changing, there are new developments for shading devices, screen printing, and so on. And the demands in the facades are getting bigger and bigger. I think it's really worth to think about new alternatives. And I think with the polyurethane, with these power cure systems, with the high strength, high elongation, high fracture energy, smaller joints, minimized frames, increased transparency, fast curing, fast on-site glazing solutions, this is really worth to think about that. So we are trying to introduce a sound experienced solution for the structural glazing application. So if you look at this train and you compare a high-rise building, you put it just upright, where is the difference? Thank you very much.
Thank you, Werner, for
questions. It's very provocative, isn't it?
right. Well, that's what we call thinking out of the box, or peeping over the fence. Are there any questions for Werner?
Sure. Yeah, Agnes.
So just to clarify, first of all, thank you, very good presentation. Just to clarify this, are you saying that there are absolutely no limits in terms of UV exposure and temperature, material temperature for polyurethane, or there are still some limitations?
No, there are still some temperature limitations.
So
I would not go beyond 80 degrees. Yeah, real temperature. Yeah.
UV?
UV, for sure. This is not changing the paradigm that this polyurethane can never be as UV resistant as a silicone, no matter what. Yeah, you can put enough scavenger in that, you will boost it no matter what. Yeah, just to make it clear, we are talking about this bomb blast resistant glazing, which happens here in this podium area. Yeah, we don't replace structural glazing silicone on the whole high-rise building. That's not our intention. We just want to think out of the box about bomb blast resistant glazing. Yeah. New provocative questions? I think we are already looking forward to the show, huh?
Everybody's thinking out of the box.
Out of this box, huh? Okay, so let me finish it. Thank you very much again.
Thank you.